Right. So welcome everybody to the this week's AI theory seminar. And today we have the pleasure of having Martina Neuman. So Martina is doing her postdoc at UWien or University of Vienna, depending how much German you speak. Right. And honestly, she works across several different areas of AI theory, from approximation theory to learning theory, collective learning stuff, to even contrastive learning. So she'll be talking about today. So without further ado, the floor is yours. Yeah. So after you, Martina.
Okay, I'm just gonna mute my video because I don't want you guys to see my forehead when I'm talking. Okay. All right, so yeah, the title of the talk is like consistency of augmentation graph and network approximability in contrastive learning, and this is joint work with Cheng Hua from Madison, Wisconsin. Okay, so I apologize for not using full screen. There's some problem with that, but I can scroll. Okay, so because the topic of the paper is about contrastive learning, so I'm going to start to discuss a little bit about it. Okay, so what is the issue? So the issue is data often arrive in high dimensions. Few are labeled and many more are unlabeled. So you can see that this can lead to opponents in learning. So you can imagine, for example, that you have like thousands of like unlabeled images, and you only have like in your training set one label image. So how can you generalize to the rest? So that's what I meant by opponents. Okay, so what is the contrastive learning? So contrastive learning is one of the modern techniques that allow you to directly manipulate the unlabeled data set. And it does so by doing two things. So first, it's gonna diversify the training set by a process of data augmentation. So by data augmentation, you can imagine something like this. You can imagine that you have like n images, little n images, okay? And then you put them through a black box process where you maybe perturb the images, or you can rotate the images, or you can change the colors of the images. At the very end, you end up with a bunch more of generated images, like big N bunch more of like generate images. I might switch little n and big N later. It doesn't matter, but at the very end, you should imagine that you have a larger set of generated images that coming from the original data image set. Okay. And then with the new kind of like more diverse and more multiple data set at the very end, you want to do the following. You want to maximize the similarity between positive pairs. So by that, I mean like, maybe two images that looking like they can be generated from the original image, then you call it the positive pair. So it's like they similarly coming from, yeah, that's what I say. They similarly coming from the same images, the original image. Then you connect them, and you also give them a very high edge weight. Now, for the pair the images that seemingly to be randomly sampled and not really connected to each other at all, you call them a negative pairs. For those kind of pairs, you still connect them, but you give it very low edge weight. So in other words, you minimize the similarity between them, okay? So in other words, you basically keep track of like how likely they are to be related to each other. And the way that you keep track is you quantify in the edge weight that you give between them. Okay. Now I hope that well for this like beginning slide, it might not be very clear, but the next slide I'm gonna give an image. I'm gonna give an example image for you. Okay. I just want to stop here and say something like this. So the process is very similar to the way that we train ourselves to see faces, right? The humans are very good at seeing faces. And the reason why is that because we are exposed constantly to different faces and also different expressions, okay? And this is a very similar process as well. You diversify yourself, you diversify orientation of the image that you see. And then you could train to contrast yourself, to contrast images against each other. So this is a part of the contrastive learning. Okay, so I hope it's clear. So the next slides I'm going to give you is this image on the internet that I saw. Okay, so this is this cluster of images is the augmented images that coming from some original image set. Okay, so you could see that, like, for example, these three cat images, they certainly that is like augmented images from this one original cat image. So you could see that, for instance, can you see my mouse, by the way?
Um, yes, yes.
Okay. And you could see that for these three cat images, they are clearly, I mean, for our eyes, for this very concrete example, they are coming from one cat example, right? From one cat image. So you could see that there is a edge between them, and the blue color signify that they have a very high edge weight between each other. And conversely, if you could see this cat image and this dog image, similar, I mean, clearly for this concrete example, they're not coming from the same image at all. They're not augmented from the same image. We still connect them, but we keep in track that they have very low similarity with each other. And so therefore, that's a negative weight, that's a negative pair, and we give it very low head weight. Okay. So I hope that like this is like clear to you about the process. So in other words, what we do mathematically is just give a weighted graph where the edge weight is going to quantify the similarity between points. Okay. All right. Now, so what's up with the theory for the contrastive learning? Well, the current theoretical framework, there's this kind of like remarkable paper, is provable guarantees for self-supervised deep learning with spectral contrastive loss by Hao Chen and collaborators. It's like 2 to 3 years ago, and it's a very remarkable paper because it's kind of established the theory of the contrastive learning, in which, so I just like you can basically paraphrase the philosophy of that paper. So in English, it means that like they philosophize contrastive learning as a spectral clustering on augmentation graph. The augmentation graph is the graph that I just described. And then they interpret the task, the contrastive learning task, as a contrastive objective on neural network representations. Now, that is a lot of English, and for me, I just need a math interpretation of that. And the math interpretation of that is that you need to do this kind of like optimization process A, okay? So in which you're trying to find a matrix n by k, so that like n by k y, so that y multiply y transpose minus ai plus this like graph Laplacian matrix. So this process is basically telling you that you would like to find the first k eigenvectors of the augmented graph Laplacians. Okay, so let me just check back with you. Is it so far okay? Is it a bit okay, or should I slow down a little bit?
Just one question, maybe for me, but I guess others might have the same question. Um, yeah, are you going to define like the augmentation graph? And if not, yeah,
Yeah,
if you,
so the
if
augmentation
you define it
graph,
later,
sorry.
yeah. Oh, if you define it later, like I won't ask now, you know?
Right, the augmentation graph is the graph that I just described. So basically just the weighted graph
Mhm.
in the previous picture. So you have the augmented data set, right? And then you just draw the connection with edges. And then you basically keep track of like, which one is the negative pairs, which one is the positive pairs. For the positive pairs, you give very high edge weights. And for the negative pairs, you give a very low edge weight.
Okay,
So that's contrastive, right? Contrast which one to be likely to be related and which one is not likely to be related.
cool.
So that's an augmentation graph, right?
Thanks.
And because now you have the augmentation graph, you certainly can talk about the augmentation graph Laplacian, right? You can put the graph Laplacian structure on that. Does it make sense?
Yeah, yeah.
Okay. So because you have like n point in the augmented set. So this graph has n nodes, right? So the graph Laplacian on the graph will be an n by n matrix. Are you familiar with the graph Laplacian, by the way?
Hmm. Me, yes, probably
Okay.
others too.
Okay, good. Then I also gonna give a definition later, but that's gonna be n by n matrix. And it's basically very similar to the adjacency matrix. It keep track of like graphing relations. Okay, so for the task A, the optimization task A, basically just trying to tell you that trying to find the first k eigenvectors of the graph Laplacian denoted by L over here. Okay, and there's this kind of like weird term that AI that you see here is just a correction term, and then the role of that I'm going to explain it later. Okay, so I hope that the task A is very clear for you. And then the task B is basically, hey, say, trying to find me a neural network that could approximate this matrix Y n by k. And again, n is a number of vertices on the graph, and k is just how many eigenvectors that you want to grab. Does it make sense now?
Yeah.
Okay. Okay. Yeah, so, all I need is just a mathematic interpretation. Oops, sorry. And once I understand that, then I understand what to do. But I also want to discuss a little bit about the philosophy of that paper. And that's a very nice paper, by the way. I should also put the side note that that is a first paper where they don't use the condition, the independent condition assumption. The independent condition assumption is some assumption that like previous papers before theirs made. In other words, that assumption is saying that like all of the augmented data sets will be independent of each other once you condition out the original data set. And that's a very huge assumption to make. So in their paper, this Hao Chen paper here, they didn't assume that, which is very nice. But in their paper, there's also a bunch more of assumptions that we seem that it's not necessary to be there. So the first assumption that is like the separability assumptions, it's saying that roughly in English is like similarity data points. For instance, like the dot images lie on the same manifold and the distinct data points like dogs versus cats lies on strictly separate manifolds. Okay, this is a very nice assumption, I think. I mean, intuitively it makes sense. But however, in the case where you'd want to do classification between images of subspecies, it might be a problem. So you can imagine that you have like um, uh, what is it, augmented images of like husky and augmented images of like malamute to be arbitrarily close to each other. So in that case, you don't really have like positive separation from each other. And yeah, by the way, the separability that is, they assume that they need a positive separation between like distinct data sets. Okay, and it doesn't really work in case that you want to separate like subspecies. Okay, I hope that makes sense. And the second assumption is the recoverability. Recoverability, it just means that like there exists a classifier that can predict labels well. For me, it just means that the task A is possible. Okay. And the third one is realizability. Realizability it means that there exists a deep neural network architecture that realizes global minimizer of the spectral contrastive loss on the augmented population data. So mathematically, it just means that B can be done. And the reason why that we saying that this assumption is not necessary and also is also quite a huge assumption to make because you don't really know, because what you try to do is that you try to approximate a k eigenvectors. You don't know like how well behaved the graph Laplacian is, and then therefore you cannot beforehand tell me about the size of like neural network that you would require. Okay, but the angle that we're coming in is that all of these assumptions are not necessary. And this is not really, this is more like for us to say that, hey, we can complete this theory a little bit more. And the way that we do that is that we interpret contrastive learning via the lens of like a manifold learning. And what we do is that we're going to analyze the consistency of the augmentation graph Laplacian, yes, in the context of manifold learning. And now I'm just going to have to explain a little bit about manifold learning. Is the speed okay? Oops, it just keep going back.
Yeah, don't worry about the speed. I guess if someone finds it hard, we'll ask questions, you know? But for me, it's
Okay.
quite good.
Okay. All right. So manifold learning is a subgroup of like graph-based learning. So it's a trigonometrically motivated graph-based learn approaches that leverage two things. One is a manifold assumption, and two is a self-supervision in high-dimensional data. So the manifold assumption is just mean that like high dimensional data tend to lie in a low dimensional structures. Okay, and mathematical model for low dimensional structures is manifold. Okay, low dimensional manifold. And the self-supervision in high dimensional data, it means that like data tend to go together. So in other words, like it's hard for you to see, let's say a data of a very sick person to be close to data of a very healthy person. Um, and when I give a talk at the University of Vienna, somebody in the audience asked, "Well, it's very similar to the separability, right?" But I would argue that self-supervision high-dimensional data is a heuristic. It does not necessarily imply that there has to be some kind of like positive distance between distinct data. Anyway, so mathematically, what does it look like? It looks like it looks like the image that I show here is also something that I stole from the internet. You imagine that you have a low dimensional manifold, and then you imagine that you sample points out of the low dimensional manifold. Okay. It's sample out of some sampling distribution. The important point is that that sampling distribution should not vanish. And once you have point on the manifolds, you want to construct graph structure. And the way that you construct graph structure is based on some kind of similarity. And what I show here is a kind of simplest similarity. So the 2 points are connected if they're close to each other, and how close it depends on how you want. Okay. And then once you have a graph structure, then you could, construct graph Laplacian. And then the next question you want to ask is that does the spectrum of the graph Laplacian capture somewhat about the spectrum of some limiting operator on the manifold? Okay, that's the end game.
That's one question, which I assume
Yeah.
at least one person has in the audience. Me. Yeah. So here, when you I guess you're doing this neighborhood graph like similarity, you know. Um, yeah. How I guess what's the standard thing to do when considering like the distance? I guess it's just the like induced Riemannian.
Yeah, it's gonna be Euclidean distance. That's a fair point to ask, because the manifold assumption that you assume that there exists a manifold, but like when you do practice, you don't know where it is, and so of course you don't know the triadic distance, and it's not gonna be fair to tell you that like connect, using the triadic distance. I mean, theoretically you can do that, but I think it's more correct to use a Euclidean distance of the ambient space.
Okay, cool. Yeah, and maybe one follow-up
Yeah.
question, but it's just purely for curiosity. So, um, yeah, how much like how important is like the Euclideanness of like for the theory? For example, like if if you had some kind of tree, maybe it's better represented in like L infinity kind of distance or something. Um, yeah, does that not like would that fundamentally like impact the theory, or is it more like a technical consequence?
It's, I would say it would be very inconvenient if you use
Okay.
like, L infinity norm, because, you could say that the moment I talk about manifold, right? Particularly when you have like smooth manifolds, you
Yeah.
want to convert the calculus of the manifold onto the calculus of the tangent space. And it's,
Yeah.
Euclidean norm L2 would be much better to handle.
Cool. Yeah, that's what I thought. Cool. Thanks, actually.
Yeah.
Cool.
Okay. All right. And this like I'm just gonna plan to like explain about 20 pages, like maybe in details, and then hopefully you get the philosophy of what I'm doing. Anyway, for this page, it's basically like most of this page I just explained. Okay, so again, the game is that first you would have to construct the graph out of the sample points, and there's multiple graphs that you could try to construct. You could try to construct the epsilon graphs very similar to what I just described. Right, the 2 points are connected to each other if they're epsilon distance away from each other. And there's also KNN graphs, and I'm not going to discuss this here, but KNN graphs is also very popular. And the way that you construct it also have levels as well. You can have like first level similarity and you can have like second level similarity. So the epsilon graph is like first level similarity. So it's like you and I are connected if we are epsilon distant away from each other. So that's a direct relationship. So first level. Now, second level similarity is like you and I are connected if we have one friend in common. So that's an indirect relationship. So second level. That's the best way I can describe it. The reason why I have to bring it up because it's really relevant to contrastive learning. Okay, now we're going to talk about the graph Laplacian that you can use. So here you could see that there's three types of like graph Laplacian that we usually use. So you have like a normalized graph Laplacian, you have like normalized graph Laplacians, and then you have like random walk graph Laplacian, and I use just a normalized one. So this is a n by n matrix, n being the number of nodes of the graph. So you have the degree matrix minus the adjacency matrix. And again, so you could see that the graph Laplacian store connections of the graph. Okay. Now, for the question of consistency of the graph Laplacian, there's tons of work in this direction. For instance, like when I start out this paper here, like graph Laplacian and their convergence on random neighborhood graphs by Hein and his collaborators say a bunch of things, and among a bunch of things is this particular thing. So when you have epsilon graphs, and you put on top of that a normalized graph Laplacians, and in the limit when n go to infinity, the number of nodes go to infinity, and epsilon go to zero, right? Because when you have more points, you have closer and closer point to you. So you want to put epsilon go to zero by epsilon go to zero as well. And by the way, epsilon here is called the graph connectivity parameter. And here the point is that you want epsilon go to zero slowly, relatively to n go to infinity. And the reason is you don't want to end up with disconnected graph, right? Because if you let epsilon go to zero very fast, you might have isolated vertex, and you don't want that. I mean, at least for analysis, right? And when you do that, then the graph Laplacian converge into this Laplace-Beltrami operator on the manifold. And you could see that this one is like a second order, right? You take the gradient and you take the divergence of the gradient. And here's a funny thing, because this operator is weighted with respect to rho, and rho here is a sampling density, okay? I would also want to say that, some technique on the market allow you to let epsilon go to zero faster than whatever threshold is allowed here, but it's not going to be a focus of mine right now. And the consistency issue, there's two consistency questions that you can ask. One is pointwise consistency, and the other is spectral consistency. And I think it has to take a few more slides for you to understand these two phrases, because if you haven't heard them before. Okay, so whenever I give talk about this paper, the paper has three theorems, and I could only get to the first theorem. So my game right now is that I'm just going to try to explain the idea behind it, the main philosophy, and then maybe I could like give a sketch of proof of the first theorem. And if I can manage up to that, I'm going to be happy. Okay, so the main game of that is that first we're going to attack the pointwise consistency. Basically, we have the graph augmentation graph Laplacian. We run n to infinity, and we want to find the limit operator because we want to know what is the expression of the limit operator. The reason why we want to do that, and this is something that, okay, so I haven't discussed why. So for the Hen et al. In our paper, where it gives the limit of like various graph Laplacian on various graph. Those type of graphs is first level similarity. The augmentation graph that we constructed, it sits somewhere between first level and second similarity. So in other words, the limit has not been explored. So we have to do this pointwise consistency to know what the limit look like, okay? And once we know what the limit look like, so we have actual concrete limit operator delta, now we're gonna talk about spectral consistency. Now, spectral consistency for us is just mean the closeness in eigenvector and eigenfunctions. So explicitly, we have the spectrum of the augmented graph Laplacian to be this like endpoint spectrum where the first eigenvalue is going to be zero. You could see that like, because you could take the first eigenvector to be like 1, 1, 1, 1, and that's going to give you a first eigenvalue to be zero. And corresponding to this like n eigenvalues is going to be the n eigenvectors. Now the spectrum of the Laplace-Beltrami operator on the manifold is going to be a counter spectrum where the first eigenvalue is going to be zero, and it's actually a simple eigenvalue and it's also isolated. And corresponding to that is going to be a countable list of like eigenfunctions. And the idea is that these eigenfunctions are smooth, okay? And then we want to show that ideally, if I take a J eigenvector, then I would be able to find a corresponding J eigenfunction so that they are closed in L2. And I say ideally because like f hat of J is, well, f hat of J lives on the graph. And the graph is not necessarily on a manifold, right? Recall that like in our setting, we have images sample out of the manifold, but then we perturb images in order to have the augmented set of data. This augmented set of data might lie outside. Well, when you perturb that, it certainly will lie outside the manifold, right? On the other hand, the eigenfunction lives on the manifold. So therefore, it has to be some kind of version of like f half of J that is approximately f of J in L2, big L2 distance. So we want to say that like these two quantities here are close to each other. In other words, like the L2, some L2 sand is going to be small, okay? Now, so once we do all of that, what do we want to conclude next? Well, because the Fj, this like a spectrum of the Laplace-Beltrami operator here are smooth, okay? In other words, I would be able to find a neural network that approximates the Fj, okay, however I want. And I would be able to have the neural network where I could also quantify the size of the neural network as well. But by triangle inequality, right, because the Fj is approximately the F hat J, so therefore the same neural network would be able to approximate the F hat J as well. So that's going to be the ultimate game. So with this kind of like conclusion on network approximability, I basically lift up the realizability. And by the way, I don't need any kind of like separability at all. And I don't even, well, I certainly also, don't even need to assume recoverability as well. So is it clear so far about the main game before I move on to the next slide?
Yeah. Yeah.
Okay. Okay, so now we're gonna discuss just a little bit. Yeah.
Sorry, I forgot. Actually, for me it's clear, but does anyone have any questions in the audience? Okay, no. So I guess we'll assume everyone is something like that. Cool.
Okay. Okay, so now we're gonna discuss a little bit about the mathematics, and as I say that I'm just gonna try to get to the gist of the first theorem. Hopefully, well, actually, I'm gonna show you all three theorems, and then maybe the technicality of the first theorem. So yeah, so of course we do analysis, and we do analysis on a manifold. So we need to put a bunch of assumptions on a manifold. Well, first of all, the manifold is going to be m dimension. It's going to be smooth manifold, orientable manifold. It's closed, meaning it have no boundary. It's a compact manifold. It's a connected manifold. You can imagine a sphere, and that's going to be okay. And then we want sectional curvatures K to be bounded above. So in other words, the manifold is not very curvy. It's not really sharply curved. And then we want a manifold reach R here to be bounded above. So the manifold reach is like how far can you go away from the manifold in order to have the projection map to be well defined. Okay, so for instance, if you have this kind of like manifold, oops, this is really bad drawing here. And you can imagine you have some point over here, and then you could see that you have two candidates for projection. But then this kind of manifold we don't consider anyway because it has the curves, and this curves right here is not really a smooth manifold. And the injectivity radius, okay, this is quite hard to describe. Um,
Can I ask one question?
Hello?
Yeah.
Yeah.
Just one question. So I'm not sure, but at least I thought usually I thought like when you have like embedded like submanifolds of like a Euclidean space, I thought that sometimes like the sectional curvature bounds will give you injectivity. Sorry, will give you manifold reach, like reach bounds. Oh, but am I wrong?
Oh, so you say that there is a relationship between K and R?
I think some bounds on K will imply some bounds on R, but I'm not sure. But I think I've read this once.
Okay, I'm not sure about that either. I thought they could be like independent from each other.
I'm not sure, but maybe it's a
Uh,
one-sided. Maybe it's not if and only if. So, I'm not sure.
okay. And the last thing is about the geometry of the manifold is that I want the injectivity radius to be bounded above. Okay, so at each point on the manifold, if the manifold are smooth, you can have a maximal radius in terms of geodesic distance, so that the corresponding geodesic ball can be uh, like diffeomorphic to an m-dimensional ball, m-dimensional Euclidean ball on the tangent plane. Okay, so in other words, there is a diffeomorphism that is changed the geodesic ball to a Euclidean m-dimensional Euclidean ball. Okay, but when you move around on the manifold, right, such such geodesic radius will change. And here the idea is that you don't want the geodesic radius to squish down to zero. So in other words, here you say injectivity radius would have to be positively bounded below. Okay, so I hope it's clear. All right, so now the talk about the sampling distribution. So there exists a sampling distribution that you can sample points out, okay? And the sampling distribution, distribution, and the sampling distribution have to have a smooth density. Actually, smooth density, so that the smooth density is going to be positive bounded below and positive bounded above. So rho mean and rho max here they both positive, okay? And here you have big N natural data points, so the original data set, where it's like sample out of this like sampling distribution, IID. And then the augmented set is like little n augmented data points. So little n here is bigger than big N, okay? And then we denote it by X bar, okay? And here we do make some kind of assumption, and then, this assumption for us is actually very natural. The assumption is that each natural datum, the original data points, each of them generates at most some number of the augmented data points, okay? And imagine something like this. Imagine that you have the augmented data set. All of them is generated from only one original data point, right? So you could imagine that like all of them is like just image of one cat shuffle around, something like that. Then you go back to you pose this problem. Okay, so it's a fair assumption to make. And besides, later we're going to use concentration theory. And if you want to use concentration theory, we have to have some kind of mild dependence among the data in order to apply the theory. Okay, so I hope it's clear. Okay, keep jumping back again. Okay, so now we're gonna discuss a little bit more about how to construct the augmentation graph. I have to prepare more in order to give you the form of the graph Laplacian. Okay, so here I've recorded the X bar is the augmented data point, and X without a bar is the original data point. And given an X bar, I say that the probability that X bar is generated from X follow a Gaussian distribution that also based on the distance between x and x bar, okay? So in other words, if x bar is very close to x, I say that x bar will have a very high chance to be generated from x. And the Gaussian distribution has a variance that is epsilon p, and I'm gonna explain about epsilon p later. There's an edge set, so now you have like x and x bar, living on this like augmented data set, and I'm gonna connect them if they are close to each other, like epsilon distant away from each other. And it does look like a first similarity, but there's more. The edge weight between x bar and x bar prime is given by this formula right over here. So take a look at this like expectation here. The pi epsilon w have the same form of the pi epsilon p, where I just exchange the epsilon p for the epsilon w. So pi epsilon w here is still a Gaussian, okay? So I just exchange the variance. So here I multiply these two quantities. The first quantity is telling me like how likely x bar is generated from x, and the second quantity is saying that how likely x bar prime is generated from x. So in other words, the product between the two telling me the likelihood that x bar, and x bar prime form a positive pair. Okay, and then I'm gonna average them all over own original data sets, expectation x falling mu. Okay, I hope this is clear. So this is like on average how likely x and x bar to be a positive pair. And there's some type of like scaling quantity here. The scaling quantity here is like, I just want my omega here to be between 0 and 1. So I decided to scale it out. And the omega, indeed, when you scale it out, is a quantity between 0 and 1, but then it becomes too small, and later I have to scale it out again. Okay, so I'm going to discuss next. There's something else here that I also want to discuss again. Oh, yeah, that's right. So you could say that the edge weight here, there is kind of like second level similarity, if you will, because the way that the likelihood between x and x bar, the edge weight between x and x bar is dictated by the third party, which is x. So therefore, that's what I'm saying, that the augmentation graph is sitting somewhere between first similarity graph and second similarity graph. It's not purely first similarity, okay? And it's gonna be reviewed more by when we find out the limits of the augmentation graph Laplacian. Okay. Okay. So I'm going to discuss a little bit more about the parameters for this. The epsilon is the epsilon that you see before, is a graph connectivity parameter is between 0 and 1. And there's some hyperparameters that we put for our analysis, eta and tau. So they're both positive here. The variance parameter, the epsilon p that you see in the previous slides, is something like this, epsilon to the tau plus 1 eta 1 root d of eta. And then you have the edge weight parameter, epsilon w, which is like epsilon to the tau, okay? Whatever it is, you just keep in mind one thing, that epsilon p would have to be much smaller than epsilon w, okay? This is not something, okay, this is originally something for us so that our analysis would go through. But then when we do the simulation, we start to realize that we do need epsilon p to be less than epsilon w. There has to be distinction between the two, epsilon p and epsilon w, in order for our experiment to go through as well. So it's also backed up by the experiment. Okay, and here the epsilon here is like, it just means the epsilon is like small enough. Can you see my mouse, by the way?
Yeah.
So here it just means the epsilon is small enough so that the analysis, like you can do local analysis. That's what it is. Okay, so the next. Okay, so here now I introduce every parameters. I can discuss about the form of the graph Laplacian. So the form of graph Laplacian, okay, applied to a function on the augmentation graph. at the augmented point x bar looking like this. So first of all, it's a summation of a bunch of difference operator. So f of like x bar prime minus f of x bar, and weighted by the edge weights between x bar and x bar prime, and then sum over all of the x bar prime in the neighborhood of x bar. Okay, and then you scale that by 1 over n. So here you could see, first of all, it looks like the average of a bunch of random variables. Okay, so you could see that the lot of large number about to come. Okay, and then it's also scaled by a bunch of things as well. So first of all, it's scaled by like epsilon w to the m. Okay, remember I told you that I want my omega to be like between 0 and 1, and I have to scale something out. It turns out that now the omega is too small. It's in the order of this, so I have to scale it out again. Okay, and then there's this thing right over here. Okay, I can explain like, the two power here. Well, as I just allude to you about, I hope I can draw something like this here. Nope, hang on a second. So as I just explained to you that, I'm gonna use a lot of large number. That's why that I decided to divide it by n. So the idea is that you want to say something like this, you want to use a lot of large number. And by lot of large number, this average is gonna be just expectation of x, okay? But in this case, expectation of x is gonna be, let's say that x is actually directly sampled out of the manifold, but the manifold has a dimension m. So in this case, it's just gonna be the integral over a ball of radius epsilon. Let's just say that like, okay. Yeah, so it's like x, okay, x. But this is a dimension m, so therefore in magnitude it's like O of like epsilon to the m. So in other words, when it's converged, it's gonna converge into something too small. That's why you have to like scale down epsilon to the m. And there's also an epsilon square here. And the reason is you want to milk out a second order structure at the end. In that case, I'm going to apply the Taylor suspension of this difference operator. Yeah, so in doing that, I have to like basically cancel out epsilon square in order to review the second order structure. Okay, so that's the idea behind it. All right, so after I do all of that, oops, hang on a second. So after I do all of that, the limit at the end, we find out to be this right here, okay? And I keep saying to you that the graph Laplacian sitting somewhere between first level similarity and second level similarity, right? Well, I would have to have a proof at the very end to back it up, okay? The limit is something like this. It's like 1/2 divergence rho square, the gradient of f.
Can I ask one quick question? I forget. Who's rho again?
Yeah.
Yeah, who's rho again?
Rho is a sampling density. Rho is a sampling density. It's introduced before. Yeah, it's always hard to like do talk on Zoom. Okay, it doesn't follow. Good, very good. So if it has been a first level similarity graph, and I'm hoping that I'll make this point clear. If it had been a first level similarity graph, it just collapsed to epsilon graph, right? Because after all, I just connect point within epsilon distance. If it has been first similarity graph, it would be predicted by this paper, right? This paper right here. And if it's predicted by this paper, then I would have to have this limit. Then I would have to have like rho out here. But in my limit, I don't have rho out here. So it's a kind of like evidence, supporting evidence that my augmentation graph, sitting somewhere between first and second similarity level graph, okay? But that also, supported by the way that we constructed anyway, because again, the edge weight between x bar and x bar prime involve the third guy, okay? So, yep, that is another point that I'm trying to make, okay? And as I say, first similarity graph, the limit of first similarity graph is like kind of well known, but like second similarity graphs or anything in between has not been like explored. I mean, has not been explored well. And okay, are we okay so far?
Yeah.
Okay.
Yeah.
Okay, so for the first point, for the first theorem, we proved the pointwise consistency. In that case, we use a lot Laplace number, but we use the quantified version of that, the concentration theory. And as I keep alluding that we apply that to a bunch of points that are not necessarily like independent of each other, but it has like some kind of like it has some kind of mild dependence among each other. So we have to apply the corresponding version of concentration theory that we actually use for Janssen. Okay, so now I'm gonna give you the full statement of like the theorem one. So this is what I mean by consistent, point-wise consistency. So again, as anything in analysis, I assume a bunch of like parameters, some kind of restricted parameter range. And I say that if F is sufficiently smooth in the tubular neighborhood of M, that will be explicit in the paper. And there's this parameter, this extra free parameter between epsilon and epsilon inverse. Epsilon here again is like graph connectivity parameter. I say that the graph Laplacian applying to F at the point x bar is nearly the Laplace-Beltrami operator, the one that you just see, applied to F at the projection point of x bar onto the manifold. Okay, so here you have x bar, and here you project it down, you have the qx bar. Okay, so that the difference between them is bounded above by this delta multiply, the some smooth norm of f. Okay, and this difference is uniform for every point in the augmented data cloud. And this event happened with probability at least 1 minus n exponent of like negative c delta square and epsilon m plus 2. Okay, alpha and beta here is some quantity, positive quantity that you can calculate. Now, let me just discuss a little bit more about this. Um, so when you take delta to be exactly equal to epsilon, this is a linear convergence in terms of epsilon. Epsilon is a graph connectivity parameter, right? So you have linear convergence in terms of epsilon, okay? Not only that, when you take epsilon is equal to delta and you want this probability to be big, so you can solve for epsilon in terms of n. So you basically set this whole thing to be little o1. When you do that, you have a range of epsilon. The range of epsilon is something like this. So log of n divided by n, the root n plus 4 up to 1. And then you could see something very peculiar. So you cannot take epsilon all the way from 0 to 1. Okay, but you can take a smaller range of epsilon from somewhere to 1. Okay, this lower threshold, when n go to infinity, will go to 0 anyway. Okay, but in this range, you would observe a linear convergence. Okay, and this lower bound is also connected to something that I said earlier. You want epsilon to go to 0 slow compared to n go to infinity. Okay, so that's a magic. Well, in this case, we just want to end up with a connected graph. Something else here I want to say, I guess. Yeah, so I think that's all I want to say for the pointwise consistency. Now, any questions so far about this?
About this? No, I think actually it's really, really nice there, you know? If I could say
Yeah.
one small thing, in the interest of time, usually we try to like, I guess, would you mind like trying to finish in
Sure. I mean, I
like
have like I guess
five-ish
I have
minutes?
like only I have only two more theorems to show. It's just like
Mhm.
gonna be statements.
That's okay,
How
that's
much
okay.
time do I have?
Yeah, so maybe like about 5 minutes.
Oh, five
Yeah,
minutes.
unless
Yeah, I can show like yeah, I can show. Yeah, I mean the theorem too is basically, what I say before, like for this paper, basically the hardest thing is just a pointwise consistency because we have to know the limiting expression. And once we know limiting expression, we basically lifting up the theories that we have before. This is just an L2 theory. It's very, it's straightforward. I shouldn't say simple, straightforward. So here I just say, if you assume a bunch of the restrictive parameter range and then you have like the augmentation graph Laplacian, you have the Laplace-Beltrami operator. Oops, I reversed that. Then with high probability, the L normalized eigenvector f hat L here is close to the L normalized eigenfunction of like the Laplace-Beltrami operator in the following sense. So here again, the FL is like operate on the manifold, but the F hat is operate on the graph. So you need to do the projection here in order to make sense. And I would have to also describe some kind of like distribution on a data cloud in order to make sense of the big L2. And then you can conclude that, the difference is like epsilon, so linear in terms of epsilon. Okay. And then like the moment that we have everything, then we could lift, for the last theorem, we could lift um, previously known theory to conclude. And here I just say a little bit about like this like optimization process here. I want to say that because you want to grab the first k eigenvectors of a normalized graph Laplacian, the trick is that you have to have a correction term so that this A here is like this big in order to grab the first k eigenvectors. If you don't have it, you might accidentally grab the last k eigenvectors instead. So that's all it is. But anyway, so the moment that we have the spectral consistency, and as I say that the spectrum of the Laplace-Beltrami operators is smooth, so you would be able to have a neural network to approximate those smooth functions anyway. So here's the idea. So yeah, so that the theorem three is conclude everything. We're saying that for the first k eigenvectors of the minimization problems that exist in real neural network, approximate that. So here the delta, little delta here, tilde delta here is the free extra parameter that you can tune. But the idea is that the layers, the number of layer of neural network is quantifiable. The upper part of that is like quantifiable. The width of the neural network is also quantifiable. And this is like okay, this is like, this is like M here is the nuclear norm. And this like little m here is the L infinity norm. So nuclear norm is just telling you like how sparse it is. So basically all of this like what is it, the quantification of like the network, the network size is quantifiable in terms of like the tilde delta and in terms of like m dimension of the manifold as well. But you could also see that the dependence on the ambient dimension is very well, it's not really what is it, terrifying. Okay.
Yeah.
Should I stop now or no?
Actually, so that would be an optimal point, mostly because if not, I will not make teaching and I'll get fired. Um,
Okay, no, it's fine. Yeah, I mean here it's just like saying tuning parameters, and then you can have something that like mitigate curse of dimensionality, and then it's done.
yeah, honestly, the talk is extremely nice, I have to say, Um, yeah, does anyone have questions? Because I think I've asked mine throughout the talk. Does anyone in the audience have questions? I'll take that as a no. That's very good silence. Okay, but very, very cool. Actually, I've wanted to read this paper in detail for a while, so this has been like really great, actually. Um, yeah. Uh, Thanks again, I guess. And
Oh,
yeah, I mean, I'll see you around. But I guess the others maybe we'll see you in the future. Cool.
okay, all right. Thank you.
Yeah, thank you,
Okay,
actually, Martina. Ciao.
okay, bye bye.